decade ago, digital forensics meant securing one piece of hardware, a desktop computer or a laptop. You seized the hard drive, cloned it, and you had the entire evidentiary universe in your hands. Today, that isolated universe does not exist. Human behavior is distributed across a continuous, decentralized network. To reconstruct an event, an investigator is no longer looking for a single object. They have to map a fractured timeline. The sequence of a person's day is split across the flash memory in their pocket, the multi-tenant cloud servers hosting their accounts, and the telemetry systems built into their car. Each of these environments speaks a different language. They run on entirely different architectures, with different retention rules and distinct physical structures. The investigative challenge is forcing these disparate systems to align into a single, verified chronology. Relying on just one source guarantees you are missing the context happening on the others. If you don't extract data across every distinct layer, the investigation is structurally blind to what actually happened. The anchor point for tracing human behavior remains the mobile phone. But getting data off a phone is not a uniform process. The volume and the specific quality of the evidence recovered depend entirely on the technical extraction method used. This diagram shows the types of data recovered by different mobile extraction methods. If we look at the logical column on the left, we see a method that relies on the device's application programming interface, or API. The forensic tool asks the operating system for data, and the OS hands over accessible user files like SMS, contacts, and call logs. Logical extraction yields parsed, readable files exactly as the user sees them on the screen. Because it communicates through the operating system, it can only see allocated space. It is entirely blind to deleted data. To go deeper, investigators must use physical extraction. The column on the far right shows how this method accesses a much broader set of data blocks. Physical extraction bypasses the operating system entirely. Instead of asking the phone for files, it connects directly to the flash memory chip and reads the raw binary data bit by bit. Reading the raw storage allows investigators to access unallocated space, the areas of memory where the operating system has marked old files as overwritten, but where the physical binary data still exists. This exposes hidden artifacts and deleted data blocks. A logical API query only provides the curated version of a device's history. To prove the actual unabridged state of a phone, investigators have to execute a deep physical extraction of the raw memory. Phones capture local activity that modern devices constantly sync to the cloud. This environment operates on a completely different architecture. You cannot seize a physical cloud server to create a one-to-one bitstream image of a suspect's data. A single Amazon or Google server hosts thousands of multi-tenant accounts simultaneously. This forces investigators to rely on remote collections, which introduces a problem the National Institute of Standards and Technology calls the metadata paradox. In a timeline reconstruction, metadata is everything. Investigators rely specifically on creation dates and last access timestamps to prove exactly when a user interacted with a file. But the act of migrating data to a cloud server or syncing it across devices actively alters those fields. When a file moves from local storage to remote architecture, the server frequently overwrites the original timestamps with the time of the transfer itself. Furthermore, to pull this data out of the cloud for a case, investigators have to use provider APIs. These collection APIs often strip certain metadata fields entirely, or normalize all localized timestamps into a single coordinated universal timecode. A physical hard drive freezes metadata in place the moment it is disconnected from power. Cloud data is highly volatile, constantly in motion, and heavily curated by the provider's automated systems. Because of this paradox, the digital collection process itself can easily cause evidence spoliation. If an investigator isn't careful, the act of downloading the cloud file destroys the timeline they are trying to preserve. You cannot take cloud data at face value. Investigators must document exactly how the API export process alters timestamps, or they risk building a timeline based on server automation rather than human action. Even with perfect extraction, phone and cloud data frequently hit dead ends. Suspects leave phones at home or delete accounts, leaving massive chronological gaps. To bridge these gaps, investigators turn to ambient connected devices, hardware that constantly records physical activity in the background. Modern vehicle infotainment systems operate as rolling data centers, continuously capturing precise logs of the car's state and its occupants. These systems record historical GPS coordinates and complete trip logs. They document the exact millisecond a driver shifts into park, or when a specific door is opened and closed. They also act as network hubs. When a mobile phone pairs with the car via Bluetooth, the infotainment system logs the connection, syncing contacts and call logs. This allows investigators to establish exactly who was physically inside the vehicle at a given location. Beyond the car, Internet of Things devices like smart home sensors or figless trackers provide a critical secondary layer of data. These wearables log involuntary physical states. In recent criminal cases, investigators have used network traffic from smartwatches to pinpoint an elevated heart rate spike, establishing the exact moment a violent incident occurred. A phone alone might tell you someone received a text. But overlaying that with vehicle telemetry and an IoT heartbeat log allows investigators to reconstruct a granular, physical sequence of events that no single device could provide on its own. Pulling data from phones, clouds, and cars gives you a timeline, but using that timeline to determine liability brings us to the ultimate requirement: legal admissibility. Because digital evidence is highly volatile, synthesizing this data is useless in a courtroom without a rigorous, documented chain of custody. You have to prove the evidence hasn't changed since the moment it was collected. This is achieved through cryptographic hashing. When evidence is collected, it is processed through an algorithm, most commonly SHA-256. This calculates the precise binary composition of the data, outputting a fixed-length string of characters. It acts as an unbreakable digital fingerprint unique to that file. If even a single bit of that data is accidentally modified during transfer or intentionally altered by a bad actor, the resulting hash will change entirely. This instantly alerts analysts that the file's integrity is compromised. Maintaining this strict verification allows investigators to adhere to the core philosophy of forensic reporting, separating technical facts from legal conclusions. A verified system artifact, like a sent email or a GPS coordinate, only proves that a specific data event occurred on a specific machine. It does not prove who was holding the device, nor does it establish human intent. Metadata indicates when a file was deleted. It doesn't tell a jury why it was deleted. This standard of proof extends to what isn't there. A sound forensic report meticulously documents negative findings, noting when a server's retention window has expired or when a phone's unallocated space has been cleanly wiped. The utility of modern digital forensics relies on precision. By extracting data across a fragmented architecture, cryptographically locking it in place, and explicitly acknowledging the limits of what that data can prove, investigators construct a factual timeline capable of surviving the strictest legal scrutiny.